So we have a quiz tomorrow, in case you guys didn't know that. It's basically on everything you could have seen in class or should have seen in class. That includes pointers, even though they're a very recent topic. You should at least understand the high levels of them. Anything that was gone over in class, you should understand for the quiz. So if you have questions on them, you can ask them now. But this is going to be a very student-led session where you guys ask questions. So hopefully people have questions. Does anyone have questions? Yes.
Can you go over pointers again?
I'll go over pointers. All of your variables necessarily live in memory, but usually you don't worry about that and you just say x plus 2 and y plus 3 and the compiler will figure out where the things are living for you. Once you're dealing with pointers, now you're explicitly using those memory addresses. So a single variable will only ever live at a single address at any given time. Now if we want to declare a pointer, what is the type going to look like? If I want to declare a pointer p, what does the type look like?
Int star p.
Yeah, so int star p. And how do I make it point to x?
Ampersand x.
So ampersand is literally called the address of operator. So when I say ampersand x, it's getting the memory address of the variable x. So now I have the pointer p, and anywhere in my code I can use star p, or I could use x. It'll be the exact same thing. So I guess star p, so what is this doing? What does that star mean?
It means the value at that.
Yeah, so if we look at it, it can be very useful to draw out the diagrams where this is a little box of memory for x, which happens to have the value 4. Then we have a little box of memory for p. And so p points to x, so we draw an arrow from p to x. So when we say star p, we're saying that go to the box that is p, star is follow the arrow, and then do whatever you want with that box right there. So I can say star p equals 7, and that'll go to the box that is x and change that to 7. Or I could say int z equals star p times 2. That's confusing because it's star star, but the one star is dereferencing p, the other star is multiplying by 2. So notice I could have just as well replaced this star p with x. You can use them in the same way. And then later on, I can have p point to a completely new thing and just say p equals ampersand z. So now p no longer points to x, it points to z, and anytime I do star z or star p, it's the same as doing z. So the useful thing about this is once we start getting into functions, so it's kind of useless to declare a pointer that points to something and then you're just dereferencing it when you could have used the original variable to begin with. But when you get into functions, so let's say we have some function int foo that takes a pointer and just does star p equals 6. So like we saw before with swap, you can't do an effective swap in a separate function by just passing integers, because everything in C is always passing by value. Even when you're passing pointers, you're passing by value. It just so happens that those values are memory addresses. So when I say foo of p, I'm passing the pointer into the function foo, and then foo is doing star p equals 6. So inside of that function, star p is still equivalent to x, but I can't use x inside of that function because it's not scoped within that function. So star p equals 6 is the only way I can access a local variable from another function. Or well, pointers are the only way I can access a local variable from another function.
And let's say you wanted to return a pointer.
Okay,
How do
so
you do that?
return a pointer as in something like in y equals 3, return ampersand y?
Yeah.
Okay. So you should never do this. So this is bad. If we get into, I think I saw in these lecture slides, you started seeing this whole diagram of memory, where like up here you get memory address 0, and down here you have memory address like 4 gigs, or 2 to the 32. So then you got some stuff, and then you have your stack. And you got your heap, which just started learning about growing up.
Isn't there a heap above the stack?
So
Yeah, the heap is on top, isn't it?
Well, he put 0 on top. Oh, he put 0.
Oh, okay.
So anywhere, disclaimer, anywhere but CS50, you're gonna see it this way.
Okay.
It's just that when you're first seeing stacks, like when you think of a stack, you think of like stacking things on top of one another. So we tend to flip this around so the stack is growing up like a stack normally would, instead of the stack hanging down.
Don't heaps technically grow up too, though?
So heaps, it depends on what you mean by define by grow up. The stack and heap always grow in opposite directions. So if the stack is always growing up, in the sense that it's growing up towards higher memory addresses, and the heap is growing down in that it's growing towards lower memory addresses. So that the top is 0 and the bottom is high memory addresses. They're both growing. It's just in opposing directions.
I just meant that because you said you put stack on the bottom because it seems more intuitive. Because this for the stack to like stack on top, but a heap's on top of itself too. So that's
Yeah.
technically
So yeah. The heap also, you think of it as growing up and larger, but the stack more so. So the stack is the one that we kind of want to show growing up. But everywhere you look otherwise is going to show address 0 at the top and the highest memory address at the bottom. So this is your usual view of memory. Do you have a question? Or?
Can you tell us more about the heap? And why?
Yeah, I'll get to that in a second. So first, going back to why returning ampersand y is a bad thing. So on the stack, you have a bunch of stack frames, which represent all of the functions which have been called. So like, ignoring previous things, like the top of your stack is always going to be the main function, since that's the first function that's being called. And then when you call another function, the stack is going to go down. So if I call some function foo, then it gets its own stack frame. It can call some function bar, it gets its own stack frame. And bar could be recursive, and it could call itself, and so that second call to bar is going to get its own stack frame. And so what goes in these stack frames are all of the local variables and all of the function arguments that any things that are locally scoped to this function go in these stack frames. So that means when I said something like, okay, so bar is a function, it's just going to declare an integer, and then return a pointer to that integer. So, where does y live?
Y lives in that bar.
Yeah. So, somewhere in this little square of memory is a littler square that has y in it. So, when I return ampersand y, I'm returning a pointer to this little block of memory. But then when a function returns, its stack frame gets popped off the stack. And that's why it's called stack. It's like the stack data structure, if you know what that is, in that or even like a stack of trays is always the example. Like main is going to go on the bottom. Then the first function you call is going to go on top of that. And you can't get back to main until you return from all functions which have been called that have been placed on top of it.
So if you did do return the ampersand of y, that value is subject to change without notice.
Yes,
right?
it's,
It could be overwritten.
yeah, it's completely, if you try and do, and this would also be an int star bar because it's returning a pointer, so its return type is int star. So if you try to use the return value of this function, it's undefined behavior because that pointer points to a bad memory.
Okay. So what if, for example, you declared int star y equals malloc size of int?
Okay, so that's better. Well, yes.
So we talked about how when we drag things to a recycle bin,
Mm-hmm.
they're not actually erased, we just lose their pointers. So in this case, do we actually erase the value, or is it still there?
So, for the most part, it's going to still be there. But let's say we happen to call some other function Baz. Baz is going to get its own stack frame on here.
Mm-hmm. And then it'll be
It's going to be overwriting all of this stuff. And then if you later try and use the pointer that you got before, it's not going to be the same value. It's going to have changed just because you called the function Baz.
But had we not, would there still be that, would we still get 3?
In all likelihood, you would.
Oh.
But you can't rely on that. / it's C just says undefined behavior.
Oh, it does, okay.
So when you want to return a pointer, this is where malloc comes in use. Where I can actually just return malloc of, say, 3 times size of int. So we'll go over malloc more in a second, but the idea of malloc is all of your local variables always go on the stack. Anything that's malloced goes on the heap, and it will forever and always be on the heap until you explicitly free it. So this means that when you malloc something, it's going to survive after the function returns.
Will it survive after the program stops running? Or?
No.
Okay, so it's going to be there until the program's all the way done running.
Yes. We can go over details of what happens when the program stops running. You might need to remind me,
Okay.
but that is a separate thing entirely.
So Mal creates a pointer though?
Yeah, so malloc.
I think malloc designates a block of memory that a pointer can use.
So let's say I want that diagram
And
again.
then
So this function
returns-
works though, because of the return?
Yeah.
It's returning the pointer.
Yeah, malloc, it
So stack.
designates a block of memory that you can use,
Mm-hmm.
and then it returns the address of the first block of that memory.
Yeah, so when you malloc, like you're grabbing some block of memory that's currently in the heap.
Right.
If the heap is too small, then the heap's just going to grow, and it grows in this direction. So let's say the heap is too small, then it's about to grow a little bit and return a pointer to this block that just grew.
Okay.
When you free stuff, you're making more room in the heap. So then a later call to malloc can reuse that memory that you had previously freed. The important thing about malloc and free is that like it gives you complete control over the lifetime of these memory blocks. Like global variables are always alive. Local variables are alive within their scope. As soon as you go past the curly brace, the local variables are dead. Mallocked variables, well, mallocked memory is alive when you want it to be alive, and then is released when you tell it to be released. So the those are actually the only 3 types of memory, really. There's automatic memory management, which is the stack. Things happen for you automatically. When you say int x, memory is allocated for int x. When x goes out of scope, memory is reclaimed for x. Then there's dynamic memory management, which is what malloc is, which is when you have control. You dynamically decide when memory should and should not be allocated. And then there's static, which just means that it lives forever, which are what global variables are. They're just always in memory. Questions?
Can you define a block just by using curly braces, but not like having to have an if statement or a while statement or anything like that?
So you can define a block as in a function, but that has curly braces too. It's
So you can't just have like a random pair of curly braces in your code that
Yeah.
would have local variables?
yes, you can.
Okay.
Like inside of int bar, we could have just say curly brace int y equals 3 end curly brace, and that's supposed to be like right here. But that completely defines the scope of int y. After that second curly brace, y cannot be used anymore. You almost never do that though. Okay, so getting back to what happens when a program ends. So there's kind of a misconception slash half lie that we give in order to make things easier. We tell you that like when you allocate memory, you're allocating some chunk of RAM for that variable. But you're not really directly touching RAM ever in your programs. If you think of it, how I drew, and actually if you go through in GDB, I'll just clear this. If you go through in GDB, you'll see the same thing. That like, regardless of how many times you run your program or what program you're running, the stack is always going to start. You're always going to see variables around address OXBFFFF something. It's usually somewhere in that region. But how can that be how can two programs possibly have pointers to the same memory?
There's some arbitrary designation of like where OFB FFF is supposed to be on the RAM that can actually be in
Yes,
different places
so-
depending on when the function is called.
Yeah, so the term is virtual memory. The idea is that every single process, every single program that is running on your computer has its own, let's assume 32 bits, so has its own completely independent address space. This is the address space. Has its own completely independent 4 gigabytes to use. So if you run two programs simultaneously, this program sees 4 gigabytes to itself, this program sees 4 gigabytes to itself, and it's impossible for this program to dereference a pointer and end up with memory from this program. And what virtual memory is a mapping from a process's address space to actual things on RAM. So it's up to your operating system to know that, hey, when this guy dereferences pointer OXBFFF, that really means that he wants RAM byte 1000. Whereas if this program dereferences OXBFFF, he really wants RAM byte 10,000. They can be arbitrarily far apart. This is even true of like things within a single process's address space. So like it sees all 4 gigabytes to itself, but let's say
Does every single process, let's say you have a computer with only 4 gigabytes in it.
yes,
Does every single process see the whole 4 gigabytes?
yes, but the 4 gigabytes it sees is a lie. It's just it thinks it has all this memory because it doesn't know any other process exists. So it will only use as much memory as it actually needs. Like the operating system is not going to give RAM to this process if it's not using any memory in this entire region. It's not going to give it memory for that region. But the idea is that, like, I'm trying to think of, can't think of like an analogy. Analogies are hard. But one of the issues of virtual memory, or one of the things it's solving, is that processes should be completely unaware of one another. And so by giving, you can write any program that just dereferences any pointer. Like just write a program that says star OX1234. And that's dereferencing memory address 1234. But it's up to the operating system to then translate what 1234 means. So if 1234 happens to be a valid memory address for this process, like it's on the stack or something, then this will return the value of that memory address as far as the process knows. But if 1234 is not a valid address, like it happens to land in some little piece of memory here that like is beyond the stack and beyond the heap, and you haven't really used that, then that's when you get things like seg faults, because you're touching memory that you should not be touching. So this is also true, like a 32-bit system, 32 bits means you have 32 bits to define a memory address. It's why pointers are 8 bytes. 32 bits are 8 bytes. So, or 4 bytes. Pointers are 4 bytes. So when you see a pointer like OXBFFFFF, that is like within any given program, you can just construct any arbitrary pointer anywhere from OX0 to OX8Fs. FFFFFF.
Wait, didn't you say they're 4 bytes?
Yeah, so
And each byte will have
hexadecimal.
We'll have
Hexadecimal 5, 6, 7, 8. So pointers you're gonna always see in hexadecimal. It's just how we classify pointers.
okay.
Every 2 digits of hexadecimal
Is 1 byte.
is 1 byte. So there's going to be 8 hexadecimal digits for 4 bytes. So every single pointer on a 32-bit system is going to be 4 bytes, which means that in your process, you can construct any arbitrary 4 bytes and make a pointer out of it. Which means that you, as far as it's aware, it can address an entire 2 to the 32 bytes of memory. Even though it doesn't really have access to that, even if your computer only has 512 megabytes, it thinks it has that much memory. And the operating system is smart enough that like it'll only allocate what you actually need, so you don't, it doesn't just go, oh, a new process, 4 gigs.
Okay.
Yeah.
What does the OX mean? Why do we write it?
It's just the symbol for hexadecimal.
Oh, it's
When you see a number start with OX,
just-
the successive things are hexadecimal.
Okay.
So you were explaining about what happens when a program ends?
Yes, so what happens when a program ends is the operating system just erases the mappings that it has for these addresses, and that's it. The operating system can now just give that memory to another program to use.
Okay.
So when you allocate something on the heap or the stack or global variables or anything, they all just disappear as soon as the program ends because the operating system is now free to give that memory to any other process.
Even though there's still values written in.
Yeah, the values are likely still there.
Mm-hmm.
It's just, it's going to be difficult to get at them.
Right.
It's much more difficult to get at them than it is to get at like a deleted file, because the deleted file is like, kind of sits there for a long time and the hard drive is a lot bigger, so like it's going to overwrite different parts of memory before it happens to overwrite the chunk of memory that that file used to be at.
Right.
But like main memory, RAM,
Mm-hmm.
you cycle through a lot faster. So it's going to very rapidly be overwritten. Questions on this or anything else?
I have questions about a different topic.
Okay. Does anyone have questions on this? Okay, different topic?
Okay, I was going through some of the practice tests, and in one of them it was talking about the size of and the value that it returns for different
Mhm.
variable types.
Yes.
And it said that both int and long both return 4, so they're both 4 bytes long.
Mhm.
Is there any difference between an int and a long, or is
So,
it the same thing?
Yes, there is a difference. So, the C standard, I'm probably gonna mess up like, the C standard is just like what C is, the official documentation of C, this is what it says. So, the C standard just says that a char will forever and always be 1 byte. Everything after that, a short is always just defined as being greater than or equal to a char. This might be strictly greater than, but not positive. An int is just defined as being greater in size, greater than or equal to a short. And a long is just defined as being greater than or equal to int. And a long is greater than or equal to long. So the only thing the C standard defines is the relative ordering of everything. The actual amount of memory that things take up is generally up to implementation, but it's pretty well defined at this point.
Okay.
So shorts are almost always going to be 2 bytes. Ints are almost always going to be 4 bytes. Longs are almost always going to be 8 bytes. And longs, it depends on whether you're using a 32-bit or a 64-bit system. So a long is going to correspond to the type of system. If you're using a 32-bit system like the appliance, it's going to be 4 bytes. If you're using a 64-bit, like a lot of recent computers, it's going to be 8 bytes. Ints are almost always 4 bytes at this point. Longs are almost always 8 bytes. In the past, ints used to only be 2 bytes. But notice that this completely satisfies like all of these relations of greater than and equal to. So long is perfectly allowed to be the same size as an integer.
Okay.
And it's also allowed to be the same size as a long. And it just so happens to be that in 99.999% of systems, it is going to be equal to either an int or a long. It just depends on 32-bit or 64-bit.
Okay. In floats, how
Mhm.
is the decimal point designated in terms of
So in
bits?
like as binary,
Yes.
you do not need to know that for CS50. You don't even learn that in 61. You don't learn that really in any course. It's just a representation. I forget the exact like bit allotments. The idea of floating point is that you allocate a specific number of bits to represent basically everything is in scientific notation.
Okay.
So you allocate a specific number of bits to represent the number itself, like 1.2345. I can never represent a number with more digits than 5. Then you also allocate a specific number of bits so that it tends to be like So it tends to be like you can only go up to a certain number, like that's the largest exponent you can have, and you can only go down to a certain exponent, like that's the smallest exponent you can have. So I don't remember the exact way bits are assigned to all of these values, but a certain number of bits are dedicated to 1.2345. Another certain number of bits are dedicated to the exponent.
Okay.
And it's only possible to represent an exponent of a certain size.
And a double, is that like an extra long float?
Yeah, it's the same thing as a float, except now you're using 8 bytes instead of 4 bytes. So you tend to use like, now you'll be able to use 9 digits or 10 digits, and this will be able to go up to 300 instead of 100.
Okay, and floats are also 4 bytes.
Yes, well, again, it probably depends overall on like general implementation, but floats are 4 bytes, doubles are 8. Doubles are called double because they are double the size of floats.
Okay, and are there double doubles?
There are not.
Okay.
I
Like
think,
long longs?
yeah, I don't think so. Yes.
On last year's test, there was a question about the main function having to be part of your program. And the answer was that it doesn't have to be part of your program. In what situation? That's what I saw.
Okay, so that
And
seems.
What
Can you-
situation?
Do you have the problem?
Yeah, I can.
Like, it doesn't have to be technically, but basically it's going to be.
I think I saw one on the different years. It was like true or false. A valid
Oh, a .c file?
CS50.c
Any .c
file
file must
Okay,
have
so
a
that's
main
separate. So a .c file just needs to contain functions. You can compile a file into machine code, binary, whatever, without it being executable yet. A valid executable must have a main function. So you can write 100 functions in one file, but no main, and then compile that down to binary. Then you write another function, another file that only has a main, but it calls a bunch of these functions in this binary file over here. And so when you're making the executable, that's what the linker does, is it combines these two binary files into an executable. So a .c file does not need to have a main function at all. And like on big code bases, you'll see like thousands of .c files and one main file. More questions?
There was another question. It was like, it said, make is a compiler, true or false? And the answer was false, and I understood why it's not like clang, but what do we call make if it's not?
So make is basically just, I can see exactly what it calls it, but it just runs commands. Make.
Script.
Oh, I can pull this. Yeah. Let's see. I'll zoom in. Okay, so. Oh yeah, make also does that. So make, this says the purpose of the make utility is to determine automatically which pieces of a large program need to be recompiled and issue the commands to recompile them. So you can make files that are absolutely huge. Make looks at like the timestamps of files, and like we said before, you can compile individual files down, and it's not until you get to the linker that they're put together into an executable. So if you have 10 different files and you make a change to one of them, then what Make's going to do is just recompile that one file and then relink everything together. But it's much dumber than that. It's up to you to completely define that that's what it should be doing. It by default has the ability to recognize this timestamp stuff, but you can write a make file to do anything. You can write a make file so that when you type make, it just CDs to another directory. I was getting frustrated because I tech everything inside of my appliance, and then I view the PDF from the Mac. So I like go to Finder, I can do go, well, connect to server, whatever. And the server I connect to is my appliance, and then I open up the PDF that gets compiled by LaTeX. But I was getting frustrated because every single time I needed to refresh the PDF, I had to like copy it to a specific directory that it could access, and it was getting annoying. So instead I wrote a make file, which you have to define how it makes things. So how you make in this is PDF LaTeX. So just like any other make file, or I guess you haven't seen the make files, but we have in the appliance a global make file that just says if you are compiling a C file, use clang. And so here in my make file that I make, I say this file you're going to want to compile with PDF LaTeX. And so it's PDF LaTeX that's doing the compiling. Make is not compiling. It's just running these commands in the sequence I specified. So it runs PDF LaTeX, it copies it to the directory I want it to be copied to, it CDs to the directory and does other things, but all it does is recognize when a file changes, and if it changes, then it will run the commands that it's supposed to run when the file changes. I don't know where the global make files are for me to check it out. Other questions? Anything from past quizzes? any pointer things? There are subtle things with pointers, like, I'm not going to be able to find a quiz question on it, but just like this sort of thing, where make sure you understand that when I say like int star x star y, this isn't exactly anything here, I guess, but like star x star y, those are two variables that are on the stack. When I say x equals malloc size of int, x is still a variable on the stack, malloc is some block over the heap, and we're having x point to the heap. So something on the stack points to the heap. Whenever you malloc anything, you're inevitably storing it inside of a pointer. So that pointer is on the stack. The malloc block is on the heap. A lot of people get confused and say like int star x equals malloc, x is on the heap. No, what x points to is on the heap. X itself is on the stack. Unless for whatever reason you have x be a global variable, in which case it happens to be in another region of memory. So keeping track, as long as like these box and arrow diagrams are pretty common for the quiz, or if it's not on quiz 0, it will be on quiz 1. You should know all of these, the steps in compiling, so you have to answer questions on those. Yes.
You go over those steps when you go to record.
Sure. So, okay, so the 4 steps in compiling, we have pre-processing, compiling, assembling, I didn't leave myself in a
Second
second.
fault.
Linking. So, pre-processing, what does that do? It is the easiest step in, well, not like, that doesn't mean it should be obvious, but like, it's the easiest step. You guys could implement it yourself.
It
Yeah.
takes like what you have in your includes and like basically copies them in and also
Yeah.
defines.
It looks for things like hash include and hash define, and it just copies and pastes what those actually mean. So when you say hash include cs50.h, the preprocessor is copying and pasting cs50.h into that line. When you say hash define x to be 4, the preprocessor goes through the entire program and replaces all instances of x with 4. So the preprocessor takes a valid C file and outputs a valid C file, where just things have been copied and pasted. So now compiling, what does that do?
Machine gun. Like it goes from C to binary.
Doesn't go all the way to binary.
To machine code then?
It's not machine
Assembly.
code. Assembly. So it goes to assembly before it goes all the way to C code. And this is like, most languages do something like this. Like, pick any high-level language, and if you're going to compile it, it's likely to compile in steps. Like first it's going to compile Python to C, then it's compile C to assembly, and then assembly is going to get translated to binary. So compiling is going to bring it from C to assembly. And the word compiling usually means bringing it from a higher level to a lower level programming language. So this is the only step in compilation where you start with a high level language and end up in a low level language, and that's why this step is called compiling.
Okay. During compiling, let's say that you've done hash include cs50.h. The compiler will that recompile like the cs50.h, like the functions that are in there, and translate that into assembly code as well? Or will it copy and paste something that's been pre-assembled?
So cs50.h will pretty much never end up in assembly.
Okay.
Okay, so stuff like function prototypes and things are just for you to be careful. Like, it's the compiler, it guarantees that the compiler can check things like you're calling functions with the right return types and the right arguments and stuff. So CS50.h will be pre-processed into the file, and then when it's compiling, it's basically thrown away after it makes sure that everything's being called correctly.
Okay.
But the functions defined in the CS50 library, which are separate from CS50.h, those will not be separately compiled. That will actually come down in the linking step.
Okay.
So we'll get to that in a second. But first, what is assembling?
Assembly to binary.
Yeah. So assembling, we don't call it compiling really, because assembly is pretty much a pure translation of binary. There is very little logic in going from assembly to binary. It's just like looking up in a table. Oh, we have this instruction that corresponds to binary 0, 1, 1, 1, 0. And so the files that assembling generally outputs are .o files. And .o files are what we were saying before, how a file does not need to have a main function. Any file can be compiled down to a .o file, as long as it's a valid C file. It can be compiled down to .o. Now, linking is what actually brings a bunch of .o files, .os, and brings them to an executable. And so what linking does is you can think of the CS50 library as a .o file. It is an already compiled binary file. And so when then you compile your file, your hello.c, which calls getString. So hello.c gets compiled down to hello.o. Hello.o is now in binary. It uses getString, so it needs to go over to CS50.o. And the linker smushes them together and copies getString into this file and comes out with an executable that has all functions it needs. So it's CS50.o. It isn't actually an O file, but it's close enough that like there is no fundamental difference. So linking just brings a bunch of files together that separately contain all of the functions I need to use and creates the executable that will actually run. And so that's also what we were saying before, where you can have 1,000 .c files, you compile them all to .o files, which will probably take a while. Then you change one .c file. You only need to recompile that one .c file and then relink everything else. Link everything back together.
Oh, we're linking. You're right. LCS50.
Yeah, so -LCS50, that flag it signals to the linker that you should be linking in that library. Questions? Have we gone over binary other than that 5 seconds in like the first lecture? I don't think so. You should know all of the big O's that we've gone over, and you should be able to kind of like, if we gave you a function, you should be able to say it's big O, roughly. Or well, big O is rough. So like, you see nested for loops looping over the same number of things, like int I is less than n, int j is less than n.
N squared.
Tends to be n squared. If you have triple nested, tends to be n cubed. So that sort of thing you should be able to point out immediately. You need to know insertion sort and bubble sort and merge sort and all of those. It's easier to understand why they are those n squared and n log n and all that, because I'm not positive. I think there was on a quiz one year where we basically like gave you an implementation of bubble sort and said, what is what is the running time of this function? So like if you recognize it as bubble sort, then you can immediately say n squared. But if you just look at it, you don't even need to realize it's bubble sort. You can just say, oh, this is doing this and this is n squared.
Are there any tough examples you would come up with, like a similar idea of figuring out?
I don't think we would give you any tough examples.
Okay.
Like the bubble sort thing is about as tough as we would go.
Okay.
And even that's like, as long as you understand that you're like iterating over the array for each element in the array, which is going to be something that's n squared.
Mm-hmm.
There are general questions like right here. We have, so just the other day, Doug claimed, I've invented an algorithm that can sort an array of n numbers in O log n time. So how do we know that's impossible? Yeah. So at the very least, you have to touch each element in the array. So it's impossible to sort an array of n. If everything's in unsorted order, then you're going to be touching everything in the array. So it's impossible to do it in less than O of n.
And you showed us that example of being able to do it in O of n if you just have if you use a lot of memory.
Yeah. And that's
That's called.
I forget what's that. Is it counting sort? That is an integer sorting algorithm. I was looking for the special name for this that I couldn't remember last week. But yeah, these are the types of sorts that can accomplish things in big O of n, but there are limitations. Like you can only use integers up to a certain number. Plus, if you're trying to sort something that's like, if your array is 0, 1, 2, negative 1, 2, 1, 5, 1, 4 million, then that single element is going to completely ruin the entire sorting. Questions? Yes.
If you have a recursive function and it just makes the recursive calls within a return statement, that's tail-end recursive. And so would that not use more memory during runtime than, or it would at least use comparable memory as an iterative solution?
Yes. So it would likely be somewhat slower, but even not really. Tail recursive is pretty good. So looking again at stack frames. So say we have main, we have int bar, say some int x or something. This isn't a perfect recursive function, but return bar of x minus 1. So obviously this is flawed, you need base cases and stuff. But the idea here is that this is tail recursive, which means that when main calls bar, it's going to get its stack frame. In this stack frame is going to be a little block of memory that corresponds to its argument x. And so let's say main happens to call bar of 100. So x is going to start out as 100. If the compiler recognizes that this is a tail recursive function, then when bar makes its recursive call to bar, instead of making a new stack frame, which is where the heaps or the stack starts growing largely, and eventually it will run into the heap, and then you get seg faults because memory starts colliding. So instead of making its own stack frame, it can realize, hey, I never really need to come back to this stack frame. So instead, I'll just replace this argument with 99 and then start bar all over. And then it'll do it again, and it'll reach return bar of x minus 1. And instead of making a new stack frame, it'll just replace its current argument with 98 and then jump back to the very beginning of bar. And those operations, replacing that one value on the stack and jumping back to the beginning, are pretty efficient. So not only is this like the same memory usage as a separate function, which is iterative because you're only using one stack frame, but you're not suffering the downsides of having to call functions. Calling functions can be somewhat expensive because it has to do all this setup and tear down and all this stuff. So this tail recursion's good.
Why does it not create new stuff?
Because it realizes it doesn't need to. Like, the call to bar is just returning the recursive call. So it doesn't need to do anything with that recursive, or with the return value. It's just going to immediately return it. So it's just going to replace its own argument and start over. And there's also, if you don't have the tail recursive version, then you get like all of these bars where when this bar returns, it has to return its value to this one. Then that bar immediately returns and it returns its value to this one. Then it's just going to immediately return and return its value to this one. So you're saving this popping all of these things off of the stack, since the return value is just going to be passed all the way back up anyway. So why not just replace our argument with the updated argument and start over? If the function is not tail recursive, if you do something like
If bar of x plus 1.
yeah. So that's, if you put it in a condition, then you're doing something with the return value. Or even if you just do return 2 times bar of x minus 1. So now bar of x minus 1 needs to return in order for it to calculate 2 times that value. So now it does need its own separate stack frame. And now, no matter how hard you try, you're going to need to, this isn't tail recursive.
When we're trying to bring up recursion, should we like aim for tail recursion? Or is it just too
In an ideal world, but in CS50 you don't have to. In order to get tail recursion, generally you like set up an additional argument where like bar will take int x int y, and y corresponds to like the ultimate thing you want to return. So then this, you're going to be returning bar of x minus 1, comma, 2 times y. So that's just a high level how you transform things to be tail recursive. But the extra argument, and then in the end, when you reach your base case, you just return y. Because y, you've been accumulating the entire time the return value that you want. You've kind of been doing it iteratively, but using recursive calls. Questions?
maybe about pointer arithmetic?
Sure.
Like using strings and
So, pointer arithmetic, when you're using strings, it's easy because strings are char stars. Chars are forever and always a single byte. And so pointer arithmetic is equivalent to regular arithmetic when you're dealing with strings. So when I say, let's just say char star s equals hello. So we have a block in memory. It needs 6 bytes because you always need the null terminator. And char star s is going to point to the beginning of this array. So s points there. Now, this is basically how any array works, regardless of whether it was returned by Malloc or whether it's on the stack. Any array is basically a pointer to the start of the array, and then any array operation, any indexing is just going into that array a certain offset. So when I say something like S3, this is going to S and counting 3 chars in. So S3, this is going to be S0, 1, 2, 3. So S3 is going to refer to this L.
And we could reach the same value by doing S plus 3 and then parentheses
Yes.
star.
So this is equivalent to S plus 3 star. And that is forever and always equivalent no matter what you do. You never need to use the bracket syntax. You can always use the star S plus 3 syntax.
And
People
so,
tend to like the bracket syntax though.
So all arrays are actually just pointers.
So there's a slight distinction when like I say int x4.
Does that create the memory?
So that is going to create 4 bytes on the stack, or 4 ints on the stack, so 16 bytes overall. It's going to create 16 bytes on the stack. X isn't stored anywhere. It is just a symbol referring to the start of the thing. Because you declared the array inside of this function, what the compiler is going to do is just replace all instances of the variable x with where it happened to choose to put these 16 bytes. It can't do that with char star s, because s is an actual pointer. It is free to then point to other things. X is a constant. You can't have it point to a different array.
Okay.
But this idea, this indexing, is the same regardless of whether it's a traditional array or if it's a pointer to something, or if it's a pointer to a Malloc array. And in fact, it is so equivalent that that is also the same thing. It actually just translates what's inside of the brackets and what's left of the brackets, adds them together and dereferences. So this is just as valid as s plus 3 star or s bracket 3.
Can you have pointers pointing to like 2-dimensional arrays?
It's harder. It's traditionally no. So a 2-dimensional array is just a 1-dimensional array with some convenient syntax. Because when I say int x3, 3, this is really just one array with 9 values. And so when I index, it correctly knows, the compiler knows what I mean by saying like, if I say x, 1, 2, it knows I want to go to the second row, so it's going to skip the first 3, and then it wants the second thing in that, so it's going to get this one. But it is still just a single dimensional array. And so if I wanted to assign a pointer to that array, I would say int star p equals x. Like the type of x is just, it's rough saying type of x since it is just a symbol and it's not an actual variable, but it is just an int star. X is just a pointer to the start of this.
Okay, and so I won't be able to access like bracket 1, bracket 2. Would that work?
I think there's special syntax for declaring a pointer, something ridiculous like int star p bracket something absolutely ridiculous. I don't even know. But there is a syntax for declaring pointers, like with parentheses and things, that it might not even let you do that. I could look back at something that would tell me the truth. But I will look for it later if there is a syntax for a point, but you will never see it. And even the syntax is so archaic that if you use it, like, people will be baffled. Multi-dimensional arrays are pretty rare as it is. You pretty much, or well, I mean, if you're doing like matrix things, then it's not going to be rare. But in C, you're rarely going to be using multi-dimensional arrays. Yeah.
let's say you have like a really long array and so in virtual memory it would appear to be all consecutive, like the elements right next to each other,
Mhm.
but in physical memory would it be possible for that to be split up?
Yes. So physical memory works, well, how virtual memory works is it just separates the unit of allocation is a page, which tends to be 4 kilobytes. And so when a process says, hey, I want to use this memory, the operating system is going to allocate it 4 kilobytes for that little block of memory. Even if you only use a single little byte in that entire block of memory, the operating system is going to give it the full 4 kilobytes. So what this means is I could have, say this is my stack. This stack could be separated. My stack could be megabytes and megabytes. My stack could be huge. But the stack itself has to be split into individual pages, which if we look at over here, let's say this is our RAM. And so like this is, if I have 2 gigabytes of RAM, this is actual address 0, like the 0th byte of my RAM. And this is 2 down here, 2 gigabytes all the way down here. So this page might correspond to this block over here. And this page might correspond to this block over here. This one might correspond to this one over here. So the operating system is free to assign physical memory to any individual page arbitrarily. And that means that if this border happens to like straddle an array happens to be left of this and right of this border of a page, then that array is going to be split in physical memory. And then when you quit the program, when the process ends, these mappings get erased, and then it's free to use these little blocks for other things. More questions?
So maybe the pointer arithmetic.
Oh yeah. So strings were easier, but looking at something like ints, so go back to int x4. So whether this is an array or whether it's a pointer to a malloc array of 4 integers, it's going to be treated the same way.
So arrays are on the heap.
Hold on. So arrays are not on the heap. This type of array tends to be on the stack, unless you declared it at ignoring global variables. Don't use global variables. So inside of a function, I say int x bracket 4. It's going to create a 4 integer block on the stack for this array. But this malloc 4 times size of int is going to go on the heap. But after this point, I can use x and p in pretty much the same ways. Other than the exceptions I said before about like you can reassign p. Technically their sizes are somewhat different, but that's completely irrelevant. You never actually use their sizes. So the p, I could say p3 equals 2 or x3 equals 2. You can use them in exactly the same ways. So pointer arithmetic now. Yes.
So do you not have to do p star if you have the brackets?
The brackets are an implicit dereference.
Okay.
So this is actually also what you're saying with the can you get multi-dimensional arrays with pointers. So what you can do is something like let's say I want int star star pp equals malloc size of int star times 5. And then I'll just write it all out first. But, okay, so what I did here is, that should be PPI. So PP is a pointer to a pointer. So you're mallocing PP to point to an array of 5 int stars. And so in memory, you have on the stack PP. It's going to point to an array of 5 blocks, which are all themselves pointers. And then when I malloc down here, I malloc that each of those individual pointers should point to a separate block of 4 bytes on the heap. So this points to 4 bytes. And this one points to a different 4 bytes. And all of them point to their own 4 bytes. So this gives me a way of doing multidimensional things. So I could say like PP3, 4. But now this is not the same thing as multidimensional arrays. Because multidimensional arrays, it translated bracket 3, bracket 4 into a single offset into the X array. This is dereferencing into the, it dereferences P, accesses the third index, then dereferences that and accesses, 4 would be invalid, the second index. So, whereas when we had the int x bracket 3 bracket 4 before as a multidimensional array, and when you double bracket, it's really only a single dereference. You're only going to you're following a single pointer and then an offset. This is really 2 dereferences. You follow 2 separate pointers. So this also technically allows you to have multidimensional arrays where each individual array is different sizes. So I think it's like jagged multidimensional arrays is what it's called, since really the first thing could point to something that has 10 elements, the second thing could point to something that has 100 elements.
Is there any limit to like the number of pointers you can have, like pointing
No.
to other pointers?
No. You can have int star 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 star, P. Back to pointer arithmetic. So,
Oh,
yeah.
so if I have int star 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 p, and then I do a dereferencing, I say like p star is equal to this value, is it only going to do one level of dereferencing?
Yes.
So if I want to access the thing that the
So let's
last
say-
pointer is pointing at,
Then you do star 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 P.
okay.
So this is P points to one block, points to another block, points to another block. Then if you do star P equals something else,
Then
then
that
you are
second arrow.
changing this, or blah. Sounds good. You're changing this to now point to a different block.
Okay.
And if these were mallocked, then you have now leaked memory, unless you happen to have different references to these, since you can't get back to those ones that you just threw away. Pointer arithmetic. So int x bracket 4 is going to allocate an array of 4 integers, where x is going to point to the beginning of the array. So when I say something like x of 1, I want it to mean go to the second integer in the array, which should be this one. But really, that's 4 bytes into the array, since this integer takes up 4 bytes. So an offset of 1 really means an offset of 1 times the size of whatever the type of the array is. So this is an array of integers, so it knows to do 1 times size of int when it wants to offset. The other syntax, so remember that this is equivalent to star of x plus 1. So this syntax also means when I say pointer plus 1, what that returns is pointer, or the address that the pointer is storing, plus 1 times the size of the type of the pointer. So if x equals ox100, then x plus 1 equals ox104. And you can abuse this and say something like char star c equals cast x to a char star. And now c is going to be the same address as x. C is going to be equal to ox100. But c plus 1 is going to be equal to ox101. Since pointer arithmetic depends on the type of the pointer that is you are adding to. So c plus 1, it looks at c, it's a char pointer, so it's going to add 1 times size of char, which is always going to be 1, so you get 101. Whereas if I do x, which is also still 100, x plus 1 is going to be 104.
Can you use like C++ in order to advance your pointer by 1?
So yes, you can. You can't do that with x because x is, again, it's just a symbol, it is a constant, you can't change x. But c happens to just be a pointer, so c++ is perfectly valid and it will increment by 1.
Okay.
If c were just an int star, then c++ would be 104. Plus plus does pointer arithmetic just as
Okay.
c plus 1 would have done pointer arithmetic. This is actually how a lot of things like merge sort, or like instead of creating copies of things, you can instead pass like if I wanted to pass this half of the array, let's erase some of this. So let's say I wanted to pass this side of the array into a function. So what would I pass to that function? If I pass x, I am passing this address. But I want to pass this particular address. So what should I pass?
Pointer plus 2.
So x plus 2. Yes. So that's going to be this address. You'll also very frequently see it as x bracket 2 and then the address of that. So you need to take the address of it because the bracket is an implicit dereference. X bracket 2 refers to the value that is in this box. And then you want the address of that box, so you say ampersand x bracket 2. And so that's how something in like merge sort, where you want to pass half the lists to something, you really just pass ampersand x bracket 2. And now, as far as the recursive call is concerned, my new array starts there. Last minute questions.
If we don't put an ampersand or a, what's that called?
Star.
Star.
Technically dereference operator, but
Dereference. If we don't put a star or an ampersand, what happens if I just say like y equals x, and x is a pointer?
so what is the type of y?
Well, let's say it's pointer 2.
So if you just say y equals x, now x and y point to the same thing.
Pointer is something. And
So
if
it's
int, and x is an int pointer.
it would complain because you can't assign
You can't
pointers.
Okay.
If you, so remember that pointers, even though we draw them as arrows, really all they store, in star x. So really all x is storing is something like OX100, which we happen to represent as pointing to the block stored at 100. So when I say int star y equals x, I'm just copying OX100 into y, which we're just going to represent as y, also pointing to OX100. And if I say int I equals casting x to an integer, then I is going to store whatever the value of OX100 is inside of it. But now it's going to be interpreted as an integer instead of a pointer. But you need the cast or else it will complain.
So wait, do you mean to cast, is it going to be casting int of x or casting int of y?
Where's what?
Okay, after these parentheses, there's going to be an x or a y there in order to.
Either. Well, x and y are equivalent.
Okay. Oh, because they're both pointers.
Yeah.
Okay.
Wait, so it would store the 100, hexadecimal 100 in integer form,
Yeah.
but not the value of whatever points to it.
Yeah. And well, the pointer. Oh yeah. So
So just
Just-
the address
yeah.
in integer form. Oh, okay.
like you could, if you wanted to, for some bizarre reason, you could exclusively deal with pointers and never deal with integers and just be like int star x equals 0, and then, well, then you're gonna get really confused once point arithmetic starts happening. So like, the numbers that they store are meaningless. It's just how you end up interpreting them. So I'm free to copy OX100 from an int star to an int, and I'm free to assign, you're probably gonna get yelled at for not casting, so I'm free to assign something like int star OX1234 into this arbitrary int star. So OX123 is just as valid a memory address as is ampersand y. Ampersand y happens to return something that is pretty much OX123.
Oh, that'd be like a really cool way to go from hexadecimal to decimal form. Like if you have a pointer and then you cast it as an int.
So you can really just print using either, so like printf, let's say I have int y equals 100. So printf %d, as you should already know, prints that as an integer. %x will just print it as hexadecimal.
Oh.
So even a pointer is not stored as hexadecimal, and an integer is not stored as decimal. Everything's stored as binary. It's just that we tend to show pointers as hexadecimal because we think of things in these like these 4-byte blocks, and like memory addresses tend to be familiar where like if it starts with BF, then it happens to be on the stack.
Sure.
So it's just our interpretation of pointers as hexadecimal. Okay, any last questions? And I'll be here for a bit after if you have anything else. So, and that's the end of that.
Yeah.